Hello, everyone. Thank you for joining us. Welcome to the Avexia webinar series. Our topic for today is TruHealth, Unlocking Insights with Epigenetic Biomarkers. My name is Christopher Chu. I am the Director of Marketing for Avexia Diagnostics and will be your host for this webinar. Today, I have the distinct pleasure of being joined by an exciting guest, Dr. Melissa Kaine, who will be our presenter for this webinar. Melissa is a geneticist with more than 10 years of genomic training and the skills to direct and interpret both clinical, cytogenetic, and molecular genetic analysis relevant to the diagnosis of management of human oncological and germline genetic disease. After her PhD, she completed a 3-year postdoctoral fellowship at Carnegie Institution for Science and co-taught practical genomics at Johns Hopkins University for 2 years. Melissa became board certified after 3 years ACGME, ABMGG clinical fellowship in laboratory genomics and genetics. Without further delay, I will now turn the webinar over to Melissa.
Hi, I'm Melissa Kaine. I'm a board certified laboratory geneticist with a PhD in molecular biology with a focus on genomics. I'm a former bioinformatician turned into a cytogeneticist and molecular geneticist. And I'm working at TruDiagnostic right now because I think that epigenetics is the future of a comprehensive clinical picture. So I want to be part of that push that gets us to that point. I appreciate everyone joining today for this webinar specifically for Avexia Diagnostics. And today I really want to talk to you about our new report that we just launched that's called TruHealth. So as many of you all probably know, TruDiagnostic's focus has really been spent on biological age and all of the lifestyle factors that go into aging. And we are the leading epigenetic age company on the market right now. You might also be aware that we really focus on the science and the research. We publish very often. We're using large databases and large data sets. And we also have great relationships with excellent academic collaborators and partners. But we're not talking about aging today, at least not directly, because we've been working on something that we think is really huge, something that we believe is going to change the face of medical diagnostics in a really big way. So if you can imagine for a minute a test that with one finger stick, ideally 5 to 10 drops of blood, that you can obtain at home that can offer you over 100 biomarkers, specific reasons for disease, and also personalized interventions to reverse or prevent disease. It exists. So this single epigenetic test reviews over 100 epigenetic biomarkers, covering a wide range of health processes like vitamins and lipids, metabolic health, immune health, neurocognitive health, certain markers for neurocognition, and then more. We put it all into an easy to read, very actionable, personalized format that's going to help you direct your patient's health like no other test. I know those are some really big claims, and I plan to back that up. But before we get in too deep into that, I just want to take a minute to review exactly what epigenetics are. So epigenetics is the study of changes in gene expression that are influenced by environmental and lifestyle factors. We're using the term epi on top of genetics being your DNA code. So you see that your genetics might not change over your lifetime. Ideally, they won't. But the way that your body expresses your genes does change. And you can kind of think of your DNA in this way as an ingredients list for a recipe. And so if DNA is the ingredient list, then epigenetics are the instructions on how to use that ingredients list to make your recipe. And depending on what instructions we use, those ingredients can create wildly different final products. So if you throw it all into a blender, you're going to get a smoothie. Apparently this one is pumpkin spice. If you put it in a crust, you're going to end up with a pumpkin pie, probably a better alternative. And it's the same principle as you can think of with cells. So if our DNA encodes certain proteins, we get a neuron, but if it encodes others, we end up with a fibroblast. And the neuron on the left here has the exact same DNA code as the fibroblast on the right, but their epigenetics differ in a really big way. The neuron needs to make different proteins from the same DNA than the fibroblast does. And that is what epigenetics controls. Epigenetics also works kind of like a light switch for each gene in your DNA. So it can turn on that gene so that the DNA is being used to make a protein, or it can turn off that gene expression so that the DNA is not making that protein. In this case, we're talking about DNA methylation because that portion of the DNA gets methylated or turned off, or unmethylated and turned on. Methylation is the addition of a molecule on the DNA at a specific location before the gene, telling the cell not to express that gene. So that molecule is a methyl group, as carbon with 3 hydrogen bonds, and that's what causes the DNA to ravel itself up. So if the DNA is methylated, it's going to ravel up into a ball and it can't be expressed, essentially blocking cellular machinery. If it is unmethylated, then it's going to be unraveled and then it can be expressed. This is sort of the simplest way of thinking about it. Basically, we are just measuring if the DNA is raveled or unraveled, expressing the gene or not. In the opposite direction. Raveled, not expressing, unraveled, expressing, to be clear. So whether your DNA is methylated in a certain location depends on a whole host of things: your parents' lifestyle, your lifestyle, what you eat, what you used to eat, how you exercise, the medications you take, and literally every factor in how you live your life now and how you've lived it up to this point. So literally everything, even listening to this presentation, could change your epigenetics. So if we think about the different omic layers available to us in laboratory medicine, we're thinking of DNA, or the genetics, the epigenetics being the gene expression, the proteomics being the product of gene expression, the metabolomics being the small metabolites. So DNA determines what your DNA code looks like, what your genes look like. Epigenetics determines which of these proteins get made, or the proteomics. And then the metabolomics are the end products of the biological pathways that the proteins control. DNA doesn't change at all, ideally, and metabolomics change very rapidly. So there's this whole spectrum of how fast these biomarkers are going to change. And proteins and metabolites are the things that we typically measure in traditional testing. So here you can see when we're talking about CRP as an example, thinking about it on the different levels. So starting with DNA, you could assess, if you're looking at DNA, this is going to be static. So you could assess if there are SNPs in the CRP gene, single nucleotide polymorphisms. That could result in a predisposition to having high or low CRP levels. You could look at epigenetics, which is going to give you an idea of where the CRP has been over the last few days to months. One example would be smoking-induced DNA methylation, and that could increase CRP expression. Proteomics are going to change from hours to days. One example would be the way in which IL-6 can induce CRP protein synthesis. So you can see CRP would peak in the blood in 24 to 48 hours after that. And then in terms of metabolomics, we're thinking of minutes to hours. This is going to be more immediate. So oxidative stress from inflammation is going to cause elevated lipid peroxidation products and then altered amino acid metabolism. So, we can choose, if we choose, measure any of these data points on this slide. So we could look at the SNPs in the DNA. We can measure epigenetics. We can measure IL-6 levels. We can measure CRP levels, lipid oxidation, et cetera. The challenge comes in when we consider timing. So if you're trying to diagnose an acute infection, maybe the protein levels would make the most sense in this case. But what if we're trying to define risk or diagnose chronic disease? The challenge is that we may only see our patients once every 6 to 12 months, and we might want a longer term picture of their CRP. So one advantage to using epigenetics in this case would be that it appears to have a longer time frame when we're evaluating a specific biological process, giving us a look into how the patient has been spending the last several months rather than just the last few hours. So considering this, we kind of imagine what it would be like to have a sort of hemoglobin A1C for every biomarker, for CRP, for white blood cell, for triglycerides. Like, What if we could understand the normalized value of that biomarker over weeks to months rather than a specific time point when the blood was actually drawn? And what we're talking about is creating epigenetic biomarkers. So we're using CRPM, which is CRP informed by methylation, instead of CRP. So epigenetic biomarkers that are trained against the actual biomarkers and the disease we are most interested in. A CRP that would kind of average all of your CRPs over the last few weeks to months rather than just an acute level. Well, what we are imagining now exists. Here's a study about that that is currently on medRxiv, but will be published. So to create these epigenetic biomarkers, we started with training an AI algorithm against the MG Biobank of 5,000 participants with all of this data here on the left side here. And then we validated the algorithm against everything you see on this right side, and then back against the MG Biobank for diseases. And for each biomarker, just like CRP, we looked at the epigenetic fingerprint for that biomarker and how it changed for the normal, the low, and the high versions of that biomarker. And we did this for 3,173 possible biomarkers, including some clinical values, proteins, and metabolites, all using a machine learning pipeline. So we started with that 3,173. You can see the breakdown there of what they are. These were all of the possible epigenetic biomarkers that we looked at, the epigenetic fingerprint of, each using an AI pipeline. And then we only kept those that we could reliably predict the correct biomarker measurement to a Spearman correlation of more than 0.2. We also did some fancy XGBoost machine learning stuff, and that allowed us to keep some of the biomarkers that initially didn't perform as well. And here's what we were left with. So these are violin plots. It's basically just a way to describe how all the biomarkers performed in terms of correlation. So we see clinical biomarkers perform the best, things like your hemoglobin A1C, your glucose, lipids, et cetera. And we had some metabolites and proteins that scored really high as well. What's interesting, though, is that a lot of the variables where we found lower correlations are tests that are only performed fasted. And because of that, we would expect more variance between the serum test and the epigenetic test. Those were things like triglycerides and lipids, et cetera. And here's what we were left with. For mortality. So we looked at how the EBP's ability to correlate to mortality, and these are volcano plots here. They sort of allow us to visualize the relationship between the hazard ratios and the statistical significance for a specific biomarker and an outcome. In this case, we're talking about all-cause mortality. So the right is positive hazard ratio, the left would be negative hazard ratio. Higher is more significant in this case. And we took that another step further. So we looked at the strongest performing epigenetic biomarkers, or EBs, for mortality. And then we found that many of them actually performed even better at predicting mortality at 15 years than their traditional testing counterparts. And the same was true for specific diseases. So for example, here is CVD, where we see the markers outperforming or performing as well as the traditional version. And again, here with neurodegeneration. So what we're learning here is that not only can we predict the traditional lab values with the epigenetic signature, but that these epigenetic biomarkers are also proving to be better in some cases at identifying risk through hazard ratios and odds ratios. But we continued our validation doing something that called gene ontology, which is just a word that means look up what these genes are doing, how they're regulated by methylation sites through an algorithm. Do they make physiological sense? Are these genes involved in biological pathways that align with the outcome that we're studying? And we found that the answer is yes. So here you can see this alkaline phosphatase M, or the methylation-derived version, is linked to corticosteroid or glucocorticoid regulation through SMAD3 and CD8A genes. And then you can see hematocrit M is linked to hematopoiesis and leukocyte differentiation. And then systolic blood pressure M, or the methylation version, associated with peptide hormone secretion pathways. And so here is some further validation using the clinical application, thinking about disease and supplement association. So you can see that the epigenetic biomarkers that are linked with conditions and supplements. So xanthan, the methylation version of xanthan, are elevated in gout. You can see omega-3 supplements increase in DHA methylation and EPA methylation. You can see how it performs in clinical panels like CMP, CBC, lipids, et cetera. They have an overall accuracy of 90% for detecting out-of-range biomarkers. And then we looked at it longitudinally as well, and we can see that the epigenetic biomarkers tracked biomarker changes over time and look at increases versus being the same versus decreases. Where you see these EBPs, they probably should now just say EBs. We used to call them epigenetic biomarker proxies, and now we just call them epigenetic biomarkers. So we found that epigenetic biomarkers are capable of predicting traditional biomarkers with exceptional accuracy, and that they can predict disease better than the traditional tests in a lot of cases and pass multiple rounds of validation. Which brings us to a dirty little secret in medicine that I learned from my medicine colleagues. No test is 100% accurate. We know this in science too. I think sometimes in medicine, it's forgotten that this is true, especially with lab diagnostics. So we get a normal CRP and we just assume there's no inflammation. I hear this all the time when I'm talking to clients about their reports. We get an elevated hemoglobin A1C and we just assume that they're headed toward diabetes or they already have it. And I think that it's easy to forget that these tests that we're kind of depending on can be wrong. So I want to take a minute and talk about biomarkers and tests in general. So a biomarker is, a measurable substance found in blood that provides information about biological processes and diseases in this case. So here's some examples for you: hemoglobin A1C, CRP, cholesterol, ApoB, et cetera. And the goal of ordering that biomarker is to diagnose disease, to predict the risk of the disease, and or to monitor the health and disease in the person. So when we're, diagnosing disease, we tend to talk about sensitivity and specificity, or we combine them and use a term called AUC, which is a combined performance metrics of both sensitivity and specificity. So here, the example would be to diagnose diabetes, use an oral glucose tolerance test. That's the gold standard with the best sensitivity and specificity. So here you can see what the sensitivities and specificities are for a random glucose test, and its AUC being 0.75 with a single blood draw. You could do hemoglobin A1C, single blood draw. It's going to be sensitive 70 to 80%, and then 60 to 85% specificity with an AUC of 0.82. Otherwise, you could try the oral glucose tolerance test, 85 to 90% sensitivity, 92 to 98% specificity, and then 0.87 on AUC. And that would require multiple blood draws over a 2-hour period. So although predictive power is important, we also have to consider precision and ease of collection. So for example, although the oral glucose test has the best OR and the best AUC, we don't often use it because of the difficulty performing the tests. It also costs 4 times more. It requires the person to have multiple blood draws and stay in the office for over 2 hours. So instead, we typically use hemoglobin A1C to diagnose diabetes because it's cheaper and quicker and still pretty reliable. But if we look at our epigenetic biomarker performance, we see that the hemoglobin A1C methylation, or hemoglobin A1C-M, performs better than both glucose and traditional hemoglobin A1C at diagnosing diabetes. And going through our paper results, it seems clear that this is the case with most of our epigenetic biomarkers. And when it comes to creating epigenetic biomarkers, we're actually not the first ones to do this. One study in the Lothian birth cohort looked at developing a CRPM from epigenetic data and found similar results as us. The CRPM was better correlated with cognitive impairment than even the traditional CRP. They also found that CRPM was more precise than traditional CRP, with a 10% improvement in precision. Another study in the same cohort found the same CRPM was more, they found the same, that CRPM was more closely associated with brain structure changes on MRI than the traditional CRP. So if we look at comparing CRP and the CRPM from that study, you'll see that CRPM performed better in terms of hazard ratios and odds ratios, better than interclass correlation or ICC, and ease of collection. So basically what we're talking about and what we've done with the TruHealth report is we've taken those 1,600 biomarkers, we've chosen 110 most clinically actionable and best performing biomarkers from the Harvard epigenetic biomarker study, and then put them into one test that costs less than $500 and can be performed with ideally single finger stick at home. And we're calling that the TruHealth report. I also, for a second, want to talk about the future directions for this. So we already know that we can assign these epigenetic biomarkers to specific diseases and that they perform better. But what would happen if we could combine multiple biomarkers and then develop a risk and disease detection tool? And that's what we're going to do for the 7 most common chronic diseases. So by combining these epigenetic biomarkers or EBs, or in this slide, EBPs, with the highest and lowest risk for specific diseases, we can then create a stronger prediction tool than anything that's currently available. So far, we've been able to hit those metrics, and we're only months away from having this test available to clients as well. And not only will we be able to use epigenetic tests to diagnose disease and identify risk, we will also be able to identify the etiology of disease to better direct care and choose interventions that are right for the individual. Here's some examples when we're talking specifically about kidney disease, one that we've been working really hard on. Right now, the world is suffering from chronic disease, most of which goes undiagnosed until too late. When we're thinking of diabetes, CAD, COPD, HF, depression, CKD, liver disease, we'll be able to diagnose these with a single finger stick and at a better test performance than what's available today with traditional testing. And it's going to save time, money, and hopefully also lives. So we think this is the future of diagnostics. It's simple, it's affordable, you can do it at home. You just need, I'd say, a little more than a few, 5 to 10 blood drops. You can more accurately diagnose 7 diseases affecting 3 billion people in the world. We're using 1,600 biomarkers that perform better than their traditional versions that normally cost, tens of thousands of dollars. And so that's what we're offering with the TruHealth test. And I want to just show you an example of a TruHealth test right now. So I'm going to pull one up. This is my colleague's result. I would show mine, but I didn't send it off till last week. And so I don't have results yet. But so I'm going to leave his name off of here, but you can see that how it looks. This is on the browser. I could have downloaded this as a PDF as well. You can see download report. You can see it that way. You can also hop around within the report as well using this left side here. But it's going to start with explaining to you what epigenetic biomarkers are. Hopefully I covered that in today's talk. But it also is going to tell you a little bit about the difference between epigenetic biomarkers versus serum levels. Also going to tell you a little bit about the cohort that we use to design these different algorithms. And then this is going to give you your biomarkers overview. So first telling you like how you look at each of the categories of biomarkers that we're measuring here, giving you, different levels based on how optimal it is. Ideally, they'll all be normal. But then it's going to have it broken down into different sections here just because it is such a big list. And you're probably going to want to go to those different topics when you see that one is particularly suboptimal. So for example, for the vitamin category, this individual is suboptimal. And so this would be like one of the first stops because probably an easy remedy. You can see also amino acids, antioxidants, fats and cellular membranes. And then we have these categorized as general health markers. It's going to include lipid peroxidation values, serum lipids, blood pressure, metabolic markers, immune markers, neurocognitive markers, inflammation markers. You can see why I didn't list all of these at the beginning when I was talking about it. And rather than listing them all right now, I'll let you read them because you can read faster than I can say them. But then paying attention to where they're falling on the percentile scale, 100% would be perfect. So you can see he's doing really well on oxidative defense. But for example, NAD metabolism is in the 29th percentile, suboptimal, and could use some help. So yeah, this is where you're going to see the top personalized recommendations. So we're using this to pick up the ones that would, would benefit the individual the most. And it's going to list those here. So you can see like the lowest hanging fruit for him is to take vitamin B2 or riboflavin. And he says that he has started that. You can see all these other recommendations from the other categories here. Valine, this oxidative stress marker that recommends taking NIC or vitamin C, but we can see these broken down further down the list here. So here again, they're talking about the risk scores for each of these individual categories to make sure that you're oriented well. You'll see anything that's normal is going to be green, out of range will be pink, and if it's critical, it's going to have this exclamation point. This is how they're going to look. In some cases, you'll see that they're normal when they're below 80%. We're not giving actual values here. We're only giving percentiles relative to the population. And then anything above 80 here is going to be deemed out of range, and it will show up like this, being pink. In some cases, being low or high is not optimal, and so only the middle will be green. And if you fall on either side, it's going to tell you that you're out of range. And likewise, there are some cases where being low is the only thing that's suboptimal. And so in those cases, you'll see out of range for those when you're low. So moving down through the vitamin category, I just want to show you how these work. If you click on an individual one, it's also going to pop down and give you a description. So we'll maybe look at the ones where he actually needs some work. So like look at riboflavin here, vitamin B2. So you can see the descriptor here, B vitamin, essential for energy production and cellular function. You can see recommendations here when you need them. So the recommendations are only going to pop up, as you can see, when you're actually either low or if you're out of range on whatever that marker is. You can click this down arrow, or you can just click anywhere on these, and this is going to drop down so that you can see it. And then in this case, the recommendations are to either supplement with riboflavin, or you can consume riboflavin-rich foods, and it gives you some suggestions for what those are. So this is a great way to really easily, your client can open this and read it and understand it. You can open it and read it and understand it. Some of these, maybe you're less familiar with, and it's going to tell you, exactly what those are in an easier kind of way to understand. And you can see all of them are going to be denoted with this italicized M, suggesting that it's informed by methylation. To be clear across the report, every single thing is informed by methylation, so we're not measuring anything this serum value. You can see vitamin B3, but B5, B6, B8, vitamin C broken down into both of these ascorbic acids, 2-sulfate and 3-sulfate here. And you can see he's low on both of these. In both cases, taking vitamin C is like the recommendation. And in these cases, you're going to see some overlap between some of these besides ones that are just like, vitamin C. But sometimes you'll see that the recommendation is the same across that, which kind of makes sense because it probably means that they need to supplement with that anyway to support both pathways. But here you can see you've got your vitamin D, vitamin E, choline, betaine, so he's low on betaine, probably a good idea to take betaine. And these two, choline and betaine, would both be a good way to think about methylation in general for an individual. Let me get down to the amino acids. So we've got a bunch of amino acids here. I'm not going to read all of them to you, but you can see like if any of them sort of fall short, it's going to recommend that that you take those. I don't think he has any of those outside the normal range, so not the best example one. But moving down to antioxidants, you'll see that some of these are going to pop up more than once. So when a category goes across, if it spans two categories, if one of these spans two categories, you'll find it in both. And that's just so that we can give you the overall range for that topic at the top, so you can pay attention to it. So like you see vitamin C pops up here too. In this case, we're doing carotenoids, but we've broken it down by lutein and also keratinidiol. Previously, we put these together in our TruAge report in one of our EBP section. And then you'll see acetyl L-carnitine. I think this one is particularly difficult for a lot of providers to recommend to clients. Like it's hard to know when it's the best time to recommend it. But you'll see that in his report, he has a couple other ones that, well, actually right here. You can see that like omega-3 would help with making acetyl L-carnitine. And also here you can see that he's low on omega-3s. So it might make sense for him to try omega-3s first and then maybe acetyl L-carnitine if he didn't want to go straight to acetyl L-carnitine. But this is sort of the way that we're thinking about it. You can see the fats and cellular membranes here. There are omega-3s, DHA, DPA, EPA, omega-6s. You've got linoleic acid, polyunsaturated fatty acids. We've got all the fatty acids here, monounsaturated, saturated fatty acids. And then all of these in phosphoglycerides, phosphatidylcholine, sphingomyelins, et cetera. Yeah, and so moving down here to the lipid peroxidation values, you can see here's one of his first examples of being high. And so in this case, maybe the best option for him would be omega-3s, but he could also try any of these other sort of methods for anti-inflammation or helping control blood sugar and things like that, but also other things that are involved in the pathway that's going to result in phospholipase A2. Here's another one that he's a little bit low on here, C18. So that's something you could pay attention to as well. And you can see that there's no recommendation for a particular supplement, but technically omega-3s could help here. And we're recommending here to get it from these foods. Down here, we have a serum lipid breakdown. So you can see all these different particles that we're putting on here, LDL, VLDL, ApoA, the HDL, and we've got total triglycerides on here as well. Here is a cool section on blood pressure. I know for a fact that mine has shown to be high from this because I had really severe preeclampsia not too terribly long ago. My blood pressure's still been up a little bit. So even from our basic evaluations early on using vanilla acetic acid and also phenylacetylglutamine, and from the TruAge report, the 4-hydroxyphenylacetylglutamine, which is not needed, really only this one is, these two together for me were super high. And if we had on there, you know, if once this moved up to this report, you can see the recommendations for change for helping improve these are pretty low hanging fruit: magnesium, B6, helping reduce your, you know, caffeine and stress and using stimulants and things like that. In this case, you can see when low levels are present. His recommendations are related for low levels. But here for low, technically this is going to help both ways, so to be fair. But here you can see like low levels here might suggest that he has insufficient phenylalanine metabolism, or that he might have some altered gut microbiome activity, which could disrupt metabolic or microbial processes. We actually see this really commonly with people who have any of these markers outside the normal range. And then we also do a systolic blood pressure here too, and this is pretty consistent, having this low systolic blood pressure and low vanilla acetic acid as well. Looking at the metabolic markers here, you can see hemoglobin A1C, glucose, fat burning marker, which is this palmitoyl carnitine, and then leptin is one of only two hormones that we're putting on this test, cortisol being the other one. And then this phenylacetylglutamine here too being a phenylalanine dysbiosis marker. In terms of the immune markers, we do an immune cell deconvolution, and these are basically representative of those in a way. And we've included some other markers too. So we've got your CRP listed here too. Here's your white blood cell count, and then neutrophil to lymphocyte. I like to think of this as a physiologic stress measure. When you're thinking of cortisol being high, that's going to cause neutrophils to be high, and then your NLR will be high. You can see systemic immune inflammation index and CD4 CD8 T cell ratio here. Moving down to the neurocognitive marker section, you'll see this memory health protein here. This is neurogranin, brain inflammation marker. You can see how they're slightly worded differently to make them easier to understand what they're for. These two dopamine metabolites, cell repair markers, and then a brain anti-inflammatory protein. Here you can see this one's related to TGF-beta. It's telling him that his is high and that he might want to consider an anti-inflammatory diet, or up his omega-3s, a theme we've seen throughout his report. In terms of inflammation markers, you'll see CRP popping up here again, but here's IL-6. Typically, if you see high IL-6, you'll see high CRP, but not always. Methionine sulfate, and then serum amyloid A1 protein, this glycoprotein, acetals. And then down here, the stress markers, here's the only other hormone that we're predicting here. You'll notice that we don't have any of the any other hormones on here right now because we're really working on them. It's a little bit more complex. It seems that in some cases it's easier for us to pick up what the endogenous hormone is doing, but it doesn't change based on even bioidentical hormones or taking certain hormones or even something to initiate different hormones. So we're working on that. Here's another adrenal activity marker and a chronic stress marker as well. Looking down here at the toxins, I think this is a super cool section. We've got some forever chemicals here, the PFAs, and this one PFOS, PFOA, and then these related to pollution and smoking. You can see HPMA. This one is the PAHs, the pesticides. That's the point of this one here. And then this bone lead predictor as well. Moving down, we've also got uric acid pathway. I'm almost done, so I know it's a really long report with this urate, xanthan M. I mentioned these earlier, allantoin, and then you've got your mitochondrial function. One way I see this one potentially being useful would be thinking about people who are taking metformin and using that. I think of metformin as being a little bit of a dirty drug in that it affects a lot of different pathways. And I think one of the things that we imagine is that we're taking it at what we call a low dose. Maybe it's not affecting other things in a negative way. But I do think that if it was impacting your mitochondrial function, you might be able to pick that up in one of these three markers here. And I think this might be a good way to sort of get an idea about how it's treating you. Okay, oxidative stress numbers here, this NPO, this oxidative stress indicator, this oxidative damage marker. Some of these are crossover from above. And then we've got the section on NAD metabolism. So you can see here he's high on this byproduct marker, which would suggest that he has inefficiency in NAD recycling. This kind of makes sense with his last marker as well, but you can see like it explains exactly how that sort of makes sense. And then tells him what he can do, lower 2-PY levels by reducing NAD supplementation. So if he was taking NAD, then he'd probably want to not take so much of it. Improving methylation or increasing exercise or fasting. And then these are the recommended things that he could take. And you probably noticed above that he was low on betaine. And so this sort of correlates with the above as well. You can see here's like the nicotinamide precursor, NR. So when we're thinking about people who are taking like NR and NMN, this is when these are the kind of markers that we really are thinking about. And then this MNA as well, where he's high as well. Down here, you've got ketones, just these two, BHBA, and then this acetoacetate. And then these are the only three supplements we're keeping around right now. So this one, important for the Krebs cycle, the spermidine, and then the last one is PEA, this fatty acid, people taking it for inflammation and pain and things like that. So I think you can see that that this report can be really useful in creating something highly personalized for your clients and coming up with a plan for not only supplementation, but maybe also for a clearer idea about diet. And in terms of thinking about retesting, because I know that this is like one of the number one questions, My current thought process is that because these are going to take a little bit more time, you're getting more of like a summary statistic for each of these measures. I think that it's a good idea to take the test either whenever you see your client first, and then maybe following up after you've started taking supplements or changed your diet, maybe 3 months later or so. I don't think I would do it closer than 2 months. And after that, ideally, you're going to get closer and closer to the goal of being optimized across the board. And following that, if you were to ask me personally, I probably would be testing more so after the optimization period. I'd probably be testing when a major life event changes, maybe major hormone fluctuations, major diet changes, major change in activity levels, anything that's really going to change the way in which you might want to optimize your supplementation. One other thought that I've had more recently, based on the changes I see in certain people's true age reports who do it 4 times a year, would be thinking about how you could modify your supplementation and diet based on the time of year, especially for those people who adjust what kinds of fruits and vegetables and things that they're taking in at each season. So I think that that could be a good approach as well. So I hope that this was helpful today, and please don't hesitate to reach out to me. My email is melissa@TruDiagnostic.com. I'm happy to help answer any questions that any of the clients for Avexia Diagnostics has. Thank you so much.
For any questions or issues you may have, please contact Avexia Diagnostics by email at info@avexiadiagnostics.com or by phone 5 days a week at extended hours, 8 a.m. to 8 p.m. Eastern Time at 888-852-2723. Thank you, Melissa, for this informative presentation. Thank you all again for joining us for this webinar event. Until next time, from everyone at Avexia Diagnostics and TruDiagnostic, stay healthy, stay safe, and we wish you all the best on your pathway to wellness.